Hey everyone, welcome to the lecture video for section 3.1 in the textbook. The theme in this section is Taylor polynomials, which are a new technique for approximating function values that we're going to learn about. We've already learned a little bit about how to approximate the area under a function or the definite integral using rectangles and trapezoids, and now we're going to learn how to directly estimate values of the function itself. So the two main things we're going to learn are what a Taylor polynomial is and how to use it to approximate a function. And then related to this, just like we learned with rectangles and trapezoids, how to compute an error bound to control for the inaccuracy in your estimation. So the first thing that I want to recall from Calc 1 is the notion of a linearization, or the tangent line approximation to a function. So you might recall that one of the applications or uses of the tangent line of the derivative was to approximate a function. If you draw the graph of a function and at a particular point, let's say x equals a, find an equation for its tangent line. It's always given by this linear equation. L of x equals f of a, the value of the function at the point, plus the slope f prime at a times x minus a, the linear term. This is a y equals mx plus b formula, by the way. This gives a good approximation of the function. So when you draw this, you'll see that close to x equals a, for nearby x values, the tangent line is a pretty decent approximation to what's happening at the on the function. However, as we move further away from the center, this x equals a, our approximation gets worse and worse. You'll notice that, and we'll explore this more in the classwork together, you'll notice that the tangent line approximation, we'll call this our first approximation, matches our function at a, and also matches the derivative of f at a. We could make better approximations if we could match further derivatives. For example, if we can match not just the slope of the function increasing or decreasing, but the concavity, concave up or concave down at a, that'll give a closer approximation, or the approximation will hug the curve better near a. So lines can't match higher order derivatives because once you take two derivatives of a linear equation, you get zero. The concavity of a line is zero. However, higher degree polynomials can do this for us, and that's the notion of a Taylor polynomial. So here's a scary looking definition, scary at first, but I hope that by the end of the video, this will be something intuitive for you to compute. And so the definition is for the nth Taylor polynomial of f of x, n will be the degree of this polynomial. At a particular value x equals a, we'll sometimes say that the polynomial is centered at x equals a. And in the formula, I just want to point out, if you see the term x minus a raised to different powers, this is an indication where the center of the polynomial is. And by definition, the nth Taylor polynomial is centered at a, is the one that shares the first n plus 1 values, derivative values with the function. And let me explain that again as we read the definition. So it's a degree n polynomial that, first of all, matches the value of the function, and past that also matches the first n derivatives of f at x equals a. So I said n plus 1. I'm starting at the 0th derivative, which is the function itself. We'll see this in some examples. And then past that, we'll take the first, the second, the third, all the way up to the nth derivative. And when we plug in x equals a, the polynomial and the original function should match values. It turns out that the following formula, and you can work this out by taking derivatives of this formula, will match all of those values, the function value and the first n derivatives at x equals a. And this is a complicated looking formula, but basically what it says is we should add up from degree 0, that's the constant term, to degree n, the highest degree term in the polynomial, some coefficients times powers of x minus a. The coefficients here we'll need to explain a little bit. The numerator of the fraction is the kth derivative evaluated at a, that's a number, and the denominator is k factorial. And if it's been a while since you've seen factorials, we've seen these once or twice this semester already, but k factorial says take the first k numbers and multiply them together. So for example, 2 factorial is just 1 times 2, which is 2, and 3 factorial is 1 times 2 times 3, which is 6. You can find tables of these, which might be useful just by Googling it. If you go to Wikipedia and search for factorial or factorial function, this will come up. So notice that Tn of x, the Taylor polynomial of degree n, is a polynomial. It's a function of x Whereas the coefficients involve function evaluations or derivative evaluations. So the numerators here are numbers, and the actual variable of the terms of our polynomial show up out here. When we plug in k equals 0, this is just a notationally efficient way of writing the polynomial, but for the k equals 0 term, we take the 0th derivative to mean don't take any derivatives, which means that evaluating that expression is just plugging a into the function. Likewise, we want the factorial function to make sense for k equals 0, and we'll just take that to be 1. There's a mathematical reason why this is the right definition of 0 factorial, which we can talk about later. So to practice with the definition, let's jump right in and compute a Taylor polynomial. In this case, we'll compute a degree 3. The highest term will be x minus 4 quantity cubed polynomial approximating y equals square root of x at x equals 4. Sometimes we'll say a equals 4, sometimes x equals 4. So let's jump right in and do this one together. If you want to go back a slide or rewind the video and write down the definition of a Taylor polynomial, I'll show you again in a moment. But you might want to pause the video now and try this on your own. Compute the things you need, assemble the whole formula, and write down a degree 3 polynomial. So I'm going to do this one for you, and I've written out a bit of information ahead of time to make our lives easier. These are things that you would need to compute yourself, though. So first of all, our formula for the third degree, the degree 3 Taylor polynomial for this function, or for any function actually, is the sum from k equals 0 to 3 of this coefficient, which we'll need to compute for each term, times x minus 4 raised to each power from 0 up to 3. So my recommendation, the way that I've learned how to solve these that I think is pretty efficient, is to write out a table. The left column will keep track of which term in your polynomial are in, k equals 0 degree all the way up to the third degree, the highest degree. Next, we'll compute the derivatives we need to eventually do function evaluations and find the coefficients. And after that, in the same table, I'm actually going to plug in the a value, in this case, a equals 4, directly into those derivatives to compute part of the coefficient. You'll see in a later problem that I'll add a fourth column where I also divide this expression in the third column by k factorial, where k increases in each step. We won't need it here because we only need to write out 3 terms. But if we want to find a formula for the whole thing, then it'll be a good idea to be able to see what the pattern is using a larger table. So in any case, I've written out the 0th through third derivative. So the original function is square root of x through the third derivative of square root of x here in the middle column. And then I've plugged in x equals 4 into each of those expressions to get the following coefficients. These will be in the numerator of our coefficients of the polynomial. And given our formula, we can now write out together what the third degree polynomial is. And I'm going to go term by term here. For the 0th expression, so I'm looking at this thing and plugging in k equals 0. The numerator is the function evaluation at 4, which is 2. The denominator is 0 factorial, which I just told you is 1. And then there's nothing after that. This is the constant term, or there are no powers of x minus 4 since k is 0. Okay, I'm going to need to shift down, but you can scroll back up, or sorry, not scroll back. You can rewind or look back one slide if you want to see the formula as we go. So the next step is to take the first degree term, which will have coefficient 1/4 in the numerator, getting that from here in the table, divided by 1 factorial, which is just 1. And in this case, we do have an x term, x minus 4 raised to the 1. Okay, let's move on to another term. The derivative evaluation for the second derivative is negative 1/32. Here we're going to divide by 2 factorial, which is just 2. And then we'll have the expression x minus 4 squared. And I need one more term. I'll sneak down here. The numerator is 3 divided by 256. Now, in this case, 3 factorial is not 3. You saw it was 1 and 2 in the first part of the sequence. It's 6. And then we'll multiply by x minus 4 cubed. I'm going to simplify this. This isn't a particularly appealing looking expression. So 2 is the constant term. 1/4 times x minus 1 to the 1 is the linear term. Let's divide this fraction and we'll get 1/64 x minus 4 quantity squared. And finally, if I cancel some powers out, let's see, I should get 1 over 512 x minus 4 quantity cubed. So this is our degree 3 Taylor polynomial that allegedly approximates values of our square root function close to x equals 4. Now, allegedly means we're going to learn about it later in the video. But for now, what you can do is check that this function, this polynomial, matches those derivatives we wrote down in the table, at least at these values. So if you take up to 3 derivatives of the polynomial we found below and plug in x equals 4, you should recover these same values in the table. I encourage you to pause the video and try this for yourself now, at least for this first example, but it'll work for any Taylor polynomial. So that's one example in the bag. Let's learn some more things about Taylor polynomials that will be useful. Oh, use it to estimate square root of 5. Sorry, I forgot to do the important part of this example, which is what's the point of a Taylor polynomial? Well, we're going to get an estimation of nearby values to the one that we know. Notice that when I plug in x equals 4, I can take the square root. I know the square root is 2, but when I plug in something nearby like x equals 5, I don't know that value off the top of my head. And in particular, without a calculator, I have no knowledge of what the answer is. However, I do know how to plug things into polynomials and get a reasonable approximation of the true answer. So what we're going to do here is square root of 5. This is close to square root of 4, which is f of 4. It's close to 2, so we'll see how close. You can see the answer here. I just wanted to compute a decimal for you, but let's plug it in and see how to get there. So this is square root of 5 is f of 5. And f of 5 is approximated by plugging in x equals 5 into the polynomial that we wrote down above. Which, if we write things out, you'll see a lot of terms actually collapse. So 2 is the constant term. If I plug in, sorry, I had a typo here. It should be a 4. If I plug in x equals 5 into each of the parentheses, then we get 5 minus 4 each time. Raised to whatever power just gives us a 1. So I'm literally just going to pick off the coefficients of this expression. And if you get a common denominator here, let's see, I forget what that is actually. Let me tell you in a moment. If you get a common denominator, it's going to be a big nasty fraction that we don't like dealing with. But you can add, in practice, you can add this up by hand. And if you did some long division and worked out a few decimal places, the denominator will be that the largest denominator is 512. You'll get, you can just start doing long division and you'll get some decimal places. I worked this out for you to get 2.2363. And I think I had to round there for the 4th decimal there. So this is an approximation to the true value of square root of 5. And at this point, you probably have a calculator or your computer handy. Punch in square root of 5 somewhere and see how many decimal places we were able to match just using a degree 3 polynomial. The name of the game with Taylor polynomials is the more terms, the larger degree polynomials we choose, the better and closer an approximation we will get. So if we wanted to better approximate square root of 5, if for some application we needed 10 decimal places of accuracy, we would want to take a higher degree polynomial. And also in practice, in the real world, we don't necessarily know how close to the true answer we got unless we have some computer or calculator to tell us the true answer, tell us the actual decimal places after 2.2363. So if we don't know that, we want a theoretical guarantee that we're within some error threshold, just like we had with our Riemann summation approximations. So that's what we're going to learn about at the end of today's video. All right, so we need to practice a little bit with summation notation. So I wanted to do this example together to practice with this notation that shows up in the definition of Taylor polynomials. We'll actually use this notation quite a bit throughout this class, but to remind you, summation notation is a compact, efficient way of writing a sum. And for now, we're going to write finite sums. This is a sum, at least for part A, a sum of 7 different terms. The later ones have different numbers of terms, but theoretically, we could also add up infinitely many terms, and that will be the notion of an infinite series that we'll learn about shortly in a few lectures. For now, let's try to write down a summation notation for each of these expressions, just to practice with this new notation. If you remember from Riemann summation, from our ways of approximating definite integrals, the summation notation was pretty central in those, even though we can write it out by hand like this. So for the key to get a summation notation is to figure out the pattern as we move along the sequence here. So from 4 to 7, just throwing some ideas out there, I see that our term increases by 3, and now I can check if that's the real pattern. From 7 to 10, we increase by 3 again. 10 to 13, increase by 3 again. Okay, so that's good. So using that idea, it looks like every term increases by 3. I'm going to start at k equals 0 and not add any 3s onto my starting 4. And I'm going to take 4 plus 3k, and then I'm going to count how many times I add 3. At 0, so 4 is adding 0 3s. This is 1, 2, 3, 4, 5, 6. So after I've added 6 copies of 3, or 6 multiples of 3, I'll stop, and then I'll get 22. So the summation notation here is the sum from 0 to 6 of the quantity 4 plus 3k, where k is that index that changes. There are other ways to write this, by the way, and I encourage you to try to, if you wrote something down before I spelled this one out for you, try to compare how our two versions connect. Also, I encourage you now that I've done one for you to pause and try B, C, and D, or at least try 1 or 2 of those on your own to see what happens. So next, let's do B together. And the key is to stare at this thing until you see a pattern. So what happens from one term to the next? Well, I start at 2, and then I get up to 6. And maybe our first guess is, well, we added 4 to get there. Well, what happens if I add 4? I only end up at 10, not 18, so that can't be the pattern. On the other hand, another way to get from 2 to 6 is to multiply 2 by 3. And if I multiply the next term, 6 by 3, I'll get 18. And you can check that if you multiply each term by 3, you'll get to the next term. So the trick here is we're going to start at 2. And then every time we multiply by a new by a new copy of 3, we're really accumulating some powers of 3. So the first term is 2 times nothing, so that'll be k equals 0. And actually, I already know I'll start it at 0. The first term after that, 6, is 2 times 3 to the 1. The next term is 2 times 3 again. You can think of each additional 3 as coming in from the right to combine with the previous 3s. And we're going to stop when we get up to, well, I don't know what 486 is in terms of power, so let's just count. Here we multiplied by 1, 2, 3, 4, 5 powers of 3. So we'll stop at k equals 5. Another way to check this is to know if you started and stopped at the right place. Well, you have to get the starting place correctly. But if you count the numbers from 0 to 6, there are 7 of them, and there are 7 expressions here. Likewise, the numbers from 0 to 5, there are 6 of them, and there are 6 expressions in part B. So let's do part C over here. So what's going on in part C? This was a little more complicated. There are a few things going on. Notice that each term, if we ignore the plus or minus sign, goes up by 1. So we can use our pattern recognition from part A to do something here. Let me write a summation symbol and leave a little space because we'll need to adjust for the plus minus. But if we start at 3 and add 1 each time, this is a sequence of values that will track what happens for the coefficient, just the positive number in each expression. And actually, let's already write down our index sequence. We start at adding nothing, so we'll start at 3 plus 0, and we'll end up at 3 plus something giving 10. That sounds like 7 to me. So we'll go from 0 to 7. That means that there are 8 terms, and you can double check there are 8 terms in part C. Now to deal with the sign. We want to flip-flop between a plus and a minus, or we start with a minus. So a minus and a plus sign. I'll show you this trick the first time, and this is a good one to copy into your brain and use on future problems is we want to take powers of -1. The nice thing about -1 is that when we multiply it by itself, you get +1. But if you multiply by another -1, you'll get back to -1. So the general pattern looks like take powers of -1, but there's a trick here. If we start with k equals 0, then all of the even powers will be positive. Whereas here, our 0, I'll circle our even terms, 0 and 2 and 4 and 6. Those terms have negative signs. So the way to adjust is to multiply by an additional -1, multiply through by a negative sign. But the way to do this in the formula is to start with -1 raised to the k plus 1. By the way, as we're writing down these formulas, the best way to check your work here is to start writing out terms. Start by plugging in k equals 0, then k equals 1, and write out each expression and check that you got the original sequence. So finally, let's do part D together. This one looks a little more complicated, but I think if we break it down into the numerator and denominator, we'll see that the patterns we've already learned help out quite a bit. So I'm not going to specify our sequence of indices yet, and we don't have to start at 0 every time. But here we notice, let's start with the denominator, just for fun, that we start with 4, we go to 9, 16, 25, 36. That looks like the sequence of squares of positive integers to me. So I'm just going to put k squared in the denominator. And here k is going to start at 2. In the numerator now, we need to be careful. We're not starting with 2, but we're starting with 1. And the sequence goes 1, square root of 2, square root of 3. What happens in the next term? That's secretly square root of 4. So this actually fits the same pattern than square root of 5. So we're taking square roots of integers. If we started at k equals 2, and the first expression is square root of 1, then we'll have to subtract 1. So this is a sequence. Again, you can plug in k equals 2 up to 6. 2, 3, 4, 5, 6. That gives us 5 terms. And you can double check by plugging in each value that this is correct. Another way to write this, by the way, if you had started with the numerator, you probably would have written down square root of k in the top. And that means that the bottom will be k plus 1 squared. That's running along a different index sequence from 1 to 5. These are equivalent expressions, and you can expand both of them and compare to see. One of the techniques that we'll learn later with infinite series and power series will be how to manipulate indices this way. But here's a brief preview of what's going on with that. Great, so let's get back to Taylor polynomials and how to write them more efficiently. So I'm going to work out the 10th degree Taylor polynomial for the function f of x equals 1 over x with center x equals 3. By the way, we know the value of this function at x equals 3. As a fraction, it's 1 over 3. But as a decimal, we know all the decimal places. It's 0.33333. It's 0.3 repeating. There are ways of working that out by hand without being told that that's the answer. And there are some clever algebraic ways. You might have seen these before. We'll see some similar things as we learn more about infinite series later. But in any case, if we know all the decimals for 1 over 3, but maybe we don't know all of them for something like 1 over 6, we want to approximate using a Taylor polynomial, we can write out the 10th degree Taylor polynomial and plug in different values of x. So let's go back to the workspace and do this one together. And if we remember from the first example we worked out for the square root of x, we needed to write down a table of all of these expressions. So I wrote out the first few for us, but it's kind of a pain to have to write out. It'll be 11 different terms if it's degree 10. So I started writing things out, and then we'll stop after a couple of these, but let's at least read these off. So I wrote down the first 3 derivatives after the original function 1 over x in this first column. Next, I plugged in x equals 3 to each of those expressions, and I got some fractions that hopefully we can guess the pattern of. And finally, actually, to make things a little easier, I took that expression and divided it by k factorial. Remember that the sequence k factorial is 1, 1, 2, 6, and then it gets larger from there. The next one will be 24. So we could keep going all the way up to 10. This column is going to be particularly annoying. Actually, really both of these are annoying because we'll start accumulating larger and larger powers of larger and larger coefficients as we bring down larger and larger powers using the power rule. So that's not particularly exciting, but we can guess a pattern for the kth term just by looking at these two terms. And this is why we practice with these pattern recognition summation formulas. So the kth derivative, it looks like what's happening each time. We certainly know that the power in the denominator increases. This is from the power rule. So after 3 derivatives, we'll have x to the 4th. That means after k derivatives, we should expect x to the k plus 1 in the denominator. Notice another thing we can actually handle right away. The plus minus, that flip-flops, and we just learned how to do that pattern. This time, for the even terms, we have a positive 1, so -1 raised to the k, not k plus 1 will be the expression. And then the challenge is to figure out what's happening in the numerator. Well, I just said this out loud. There's a sequence we know that starts 1, 1, 2, 6, and that's the factorial sequence. And it actually starts at, if you see 1, 1, and then 2, you'll see here's 2 factorial, 3 factorial. We actually started at k equals 0 with 0 factorial. So that's actually the expression for the kth derivative of 1 over x. And this is true, regardless of what trying to compute a Taylor polynomial. So that's a good formula to have. And if you don't remember that formula, and I actually never remember this formula, it's a good idea to try to derive this using the pattern recognition that we just practiced. So we've got our kth derivative. If we plug in x equals 3 now to this formula, we'll get the kth derivative evaluated at 3. So we're not plugging anything in for k. K remains an unknown. I call it an index. It's like a place counter. And then in the denominator, we just have 3 raised to the k plus 1. And here's the nice part. We need to take this whole expression, the kth derivative evaluated at 3, and divide by k factorial. What happens is that's going to cancel out this k factorial in our third column, just to give us -1 to the k divided by 3 to the k plus 1. And if you start plugging in k values, you'll see that you match these first 4 terms that we worked out in the table above. Another way to do this, by the way, is this is the only thing that we actually need for writing down the Taylor polynomial. So if you're not able to recognize the patterns in the second and third columns of the table, but you're able to recognize the pattern in the third part of the table, then that will be good enough to write down the Taylor polynomial representation. The reason that I write this table with all 4 columns, by the way, is just in case I start filling things out and I can't figure out these patterns, I don't need to do that much. I just need to write the first few terms in the final column and use that to find the pattern of the coefficients for Tn. So let's write out T10 as a compact formula. It's going to be a sum from 0 up to 10. It's a degree 10 polynomial. And the coefficient is this expression right here. So let's copy that in. -1 to the k divided by 3 to the k plus 1. And I'll write out a few terms. I'm not going to write all of them. And actually, you can go look at the table to see that these are correct. I'll just cheat a little bit. The constant term here is 1/3. The linear term is -1/9 times x minus 3. The quadratic term is 1/27 x minus 3 squared. And I'll stop there. We can, the cubic term, here's the coefficient if you want. We'll go up to the 10th term, which is +1 over 3 to the 11th, which, I don't know that power, but we'll leave it like that, times x minus 3 to the 10th. So there's our degree 10 polynomial. And theoretically, if you wanted to find an approximate value for 1/6 as a fraction, it's something you can do long division and get a few decimal places for. Or if you know the tricks to find repeating decimal expansions, you can do it that way. But in this case, you can plug things into T10 here and get a decent approximation. Good, so there's 2 examples down. We'll have lots and lots of practice with this, but at this point, actually, you can take any function you like, pick a target, say, x equals something nearby a thing that you know, so center it at a value that you know for the function, and then start writing down any polynomial terms that you can think of in order. So for the rest of the time, I want to discuss how to understand the accuracy of our Taylor polynomial approximation. There are going to be some proofs on these slides, and I'm going to skip over them. They're also in the textbook, but I encourage you to look through carefully and see if you can reason through these next few results that we'll discuss. So to assess how accurate the Taylor polynomial approximation really is, we want to think about when functions match values, or really more importantly, when they match their derivative values on a certain interval, how the functions relate to each other. So if we know about the increasing or decreasing behavior between, if we can compare the increasing or decreasing between two functions, can we compare the original function values of those functions? So to set things up, if we have two differentiable functions, f and g, and we look at their values on an interval from a to b, where the left endpoint, the starting value, they match. So f of a equals g of a. The theorem has two parts. First of all, if the derivatives match on the entire interval, if the first derivatives have the same value, the slopes of tangent lines are equal everywhere, then that's actually good enough to deduce that the functions are identical on that interval. So if two functions start at the same place and have identical slopes over some interval of values, then they are the same function, which is already pretty interesting, I think. We just need one derivative to deduce that. Next, and more useful for us, is if one function has a smaller derivative than the other, the slopes of f are shallower than the slopes of g on this entire interval, then the function values of f have to stay below the function values of g on this interval. And we threw in a parentheses here since we know that at the left endpoint they are equal. But it's a strict inequality. The function g will actually be above the function f. We'll see a picture of this in a moment. So the intuition here is, in words, think about growth rate, the derivative as the rate of change. If one function grows faster than the other, it should lie over that function. It should have a higher value. The formal proof of this, by the way, uses the fundamental theorem of calculus. So here's the statement. I encourage you to read this for yourself to justify it. Here's the picture I was talking about. Here's an expression. Here's a figure where f and g are two functions. They both match at x equals a. G clearly has larger derivative values. The slope is steeper moving from a to b than f does. And the entire function g is lying over the function of f except at the point that they match. So how this works for Taylor polynomials, we're going to define the following expression, r sub n of x, as a function of x that gives the remainder at any x value. What this means in plain English is if we use a Taylor polynomial Tn to approximate a function f of x, then Rn is the function that measures the distance between the polynomial approximation and the true function at x. It's the remainder, it's the error term. And by the way, there's a sign convention here. We'll generally take absolute values and ignore this. But if you want to talk about the true error and also know if it's above or below, rather if you're under or overestimating, then Rn of x is the function that gives the negative of the error, where a positive error means that we overestimated and a negative error means that we underestimated. If you write out the definition for Rn, by the way, you'll see pretty directly that if f is larger than Tn, that said that Tn was an underestimate and vice versa. So here's the trick. We want to know the value of Rn. We actually want to control this error term, this remainder expression Rn of x, in order to guarantee that we're within certain error thresholds, like we've done with rectangles and trapezoids. And we're going to use that derivative comparison theorem in a clever way here. The point of Tn, again, is that it matches derivative values of f of x for all derivative levels up to the degree Tn. So the two arguments that we're going to use based on the previous slide are that if we can first bound the next derivative of the function, the first one that doesn't match our polynomial, then we can actually use it to compute Rn exactly. Sorry, if we know the next derivative, not just bounded, if we know it's some constant m, then we can compute Rn exactly. But in practice, that's difficult or impossible to achieve. So instead, if we have a moving n plus first derivative, but we can bound it on our interval of estimation by some capital M, then the error will be boundable as well. We'll have an expression just like our Riemann summation error bounds that will control our error in terms of that capital M. So this is one of the slides where there's a proof. I'm not going to talk about the flow chart down below, but you can read this through. This is a mathematical proof of the following theorem that says that if the n plus first derivative of x is constant, and we need a function that has that many derivatives, that's n plus first or n plus 1 times differentiable. If that function is a constant function on a plus b, then f of x is actually given to us by a polynomial. It's equal to the n plus first Taylor polynomial. And if we don't want to write that out, the fast way to write it is we already have the nth approximation, Tn, and we just add the last term, which is m divided by n plus 1 factorial times x minus a to the n plus 1 power. This is just a slight way to rewrite the definition of the n plus first polynomial. And if you look closely, the numerator here is the n plus first derivative evaluated at a, since this is a constant. This theorem, again, is not so helpful for applications, because if our function already was a polynomial, we probably would have known that. And if we didn't know it, then we would discover by taking n plus 1 derivatives and getting a constant. The only functions, this is a useful fact to think about in its own right, the only functions that have constant derivatives are linear polynomials. This is actually a consequence of the fundamental theorem of calculus part 2, that any antiderivative has to be of the form linear plus constant. Great, so this theorem is useful for us because if we don't have a constant n plus first derivative, we can still settle for an error estimation or an error inequality. And this theorem is called Taylor's inequality. This is one that we're going to use for the rest of the video and a lot in class in applications. If instead of having a constant n plus first derivative, we can bound that derivative by capital M, and really we're going to bound the values of f to the n plus 1 between m and negative m. The way to write that is the absolute values stay less than m. For all x between some a and some b, then if we center our polynomial at x equals a, and we want to estimate at values between a and b, the error expression Rn at any of those x values between a and b is bounded in absolute value by this, this last term of the t to the n plus 1 polynomial. So here we'll use the bound on derivative values divided by n plus 1 factorial times the x minus a term, and we'll stick it all in absolute value. So we're just getting an absolute value or a positive number estimate here. Here's a proof that this bound is correct by comparing derivatives with the worst case scenario, which is the bounded version of the n plus first polynomial. I'm not going to talk through this flow chart again, but you can pause the video here, or you can go look up the proof in the textbook. This is also a proof slide, so we need to actually we need to further bound the two expressions we have in mind, Rn and f of x. And I'm going to skip through all of that and go straight to example. So in this example, we're going to study the sine function. We're actually going to work out a formula for its Taylor polynomials in general. And then we're going to do some other things involving bounding error for this expression. All right, let's do it. I've written out a few terms again for us. To find the nth Taylor polynomial, remember that each term will have a coefficient that looks like the kth derivative of value at, oh, I didn't even say this, by the way. We're going to center our polynomial at x equals 0, since we know sine of 0 equals 0. Each term will look like some derivative evaluated at 0 divided by k factorial. So first I'm going to start taking derivatives. Sine's derivative is cosine, whose derivative is negative sine, whose derivative is negative cosine, and then we actually wrap back around. So this is a nice pattern when we have this this cyclic pattern that repeats only 4 times, or repeats every 4 derivatives. This will make it easier to deduce the general formula. If we plug in x equals 0 to each of these derivatives, we'll get a 0 for the sine expressions and a plus or minus 1 for the cosine expressions. So notice that every other term drops out. And in other words, we only need the odd terms when we write down our polynomial. So this is a polynomial in the end that only has odd degrees of x. I'll take a drink of water while you look at how I got the third column here. So in the the fourth column. So in the fourth column, as we did in the last example, we're just dividing the expression in the third column by k factorial. The zeros stay 0. For k equals 1, we'll get 1 divided by 1. And for k equals 3, we'll get -1 divided by 3 factorial, which is 6. The trick here is to work out some pattern for these expressions. Notice that I separated things into two cases, which, if you haven't seen this notation used before, these are compact ways of writing all even and all odd numbers. So for things of the form 2 times k, those are all the even numbers. Notice that all of the derivatives there are plus or minus sine of x, and we can actually say which plus or minus it is if we have we have something that's 0 or 4 or 8, a power of 4 in other words, or a multiple of 4 in other words, then we'll have positive sign. And that's when 2k is divisible by 4, which means that k has to be divisible by 2. And that means that it switches every time k becomes even. So the way to write this is -1 raised to the k. On the other hand, so when you plug in k odd and you double them, for example, 2 times 1, that's 2 times k equals 1. That'll give us a negative sign. So this is the correct pattern. On the other hand, for the odd terms, the odd degree terms, we always have a cosine. And here we need to be a little careful. If I start at the, I guess I've reused my k, unfortunately. I'm sorry about that. I'm going to work things out with k. So below this line, k means something a little different. So for the cosine terms, if I plug in k equals 0 to this expression, that gives me the degree 1 term here. And that should be a +1. So that's going to be -1 to the k once again. So these are at least consistent. Now here's the trick. For all of the even terms, the derivative evaluations at 0 are 0. And for all of the odd terms, let's just plug it into this formula now. We can start working just in the bottom of the table. For all of the cosine terms, it'll be -1 to the k times cosine of 0 is +1. So you just get the sign flipper term. Finally, we're going to take each of these and divide by the correct factorial. For the even terms, there's nothing in the numerator. So those just vanish. They don't show up in the polynomial. And for the odd terms, we'll take the total degree and its factorial will show up in the denominator. Now, I encourage you to pause the table, pause the video and check this table, check the first few values and compute a few more past the third degree term if you want to check that this pattern is correct. This is a more complicated pattern than we've seen before, since there's a counter here for only tracking odd numbers that separately is tracking whether or not it's positive or negative. And that's what we're going to use to write down our Tn of x expression. So Tn of x, the degree n polynomial. This is the polynomial that needs to have degree n. And the way we're going to do this is we're only going to count through the numbers that show up in this table, like 2k plus 1. We can keep track of odd numbers by plugging in increasing values of k there. So if we start at k equals 0, that starts the odd number here at n equals 1. And we're just going to write down the expression that we had above in the bottom right, -1 to the k times 2 to the k plus 1 factorial times x to that same degree, x to the 2k plus 1. The trick here, and I wrote it out for you ahead of time, so you can think about it while I was writing, is where to stop this. We don't want to go up to k equals n, in which case we would have a 2 to the n plus 1 degree polynomial. But instead, we want to take n and chop it in half. Now, if n is even, we'll just divide by 2. If n is odd, we want to divide by 2 and round down to the nearest even into, sorry, actually, is that correct? Yeah, we want to round down. We want to round down to the nearest integer so that 2 times that is the largest odd power below n. So another way to write this is go up to m, where m is equal to 2m, where 2m plus 1 is equal to n, or n minus 1. Okay, so this is our expression for the degree n Taylor polynomial for the function sine of x. Now, in order to estimate the error, I want to step you through a few steps here, estimating the error of this Taylor approximation for any n. How can we bound the derivatives of the function? Well, notice that our derivatives, go back to the table, are all plus or minus sine or cosine. And the nice thing about sine and cosine is they're all bounded by, they slingshot back and forth between plus and minus 1 on the graphs of these functions. So we can bound them and all of their derivatives by positive 1 in absolute value. So that's an easy error bound. So we can plug in m equals 1 into our error bound formula. And I just want to analyze what happens in this formula. So if we look at this formula for some n and for some x value that we want to plug into sine to estimate, we want to understand what happens to the error as we change those parameters. So if we fix n, the degree of the polynomial, let's say we write down t10 again, but for this function, and we increase x, we move further away from 0, in other words. Here's where we know the value. And as we move the x value to the right and we approximate this sine curve with our degree n polynomial, what happens to the error here? Well, if n is fixed and x is increasing, we can take a limit as x goes to infinity if you want, but this expression here will increase. So the whole thing increases as x increases. In other words, the error, in theory, can get larger, and in practice, it does get larger as x gets further away from 0, where we centered our polynomial. So as we move out, and you can do this by shrinking x by going into the negatives as well. As we move further away from the center of the polynomial, the error can increase, and in practice, it does. If you think about it this way, all polynomials go off to infinity at either end. No polynomials have any asymptotes. So it either goes to plus or minus infinity, depending on the leading sign. And sine and cosine functions are bounded between 1 and -1. So any Taylor polynomial will eventually be a terrible approximation. We'll have, in the limit, infinite area as we move from the center. On the other hand, what happens to this error bound if we fix the value x, but increase the number of, or the degree of the polynomial that we use to approximate it? So what happens to n plus 1? What happens to the error term as we increase n? Well, the key here, and really if we, I'll throw some absolute values here just to force our numerator to be positive as well. What happens to these expressions as we increase n? Well, to go from the left to the right expression, this is just bumping n up by 1, we really added, or I shouldn't say added, we multiplied an additional power of x in there. On the other hand, in the denominator, what do you do to go from one number's factorial to the next? Well, n plus 1 factorial is multiply everything from 1 up to n plus 1. N plus 2 is the same thing, except keep going and multiply in n plus 2 as well. Sorry, that got a little scratchy there. N plus 2. And the trick now is this expression is identical to the one that we had over here. So these are the same. So what happened when we increased n by 1 is we threw in a new factor of x and a new factor of n plus 2. and n is increasing, x is staying the same, so the denominator is getting larger. And in this case, the error goes to 0. So the way to interpret this in plain English is if we fix an x value that we want to approximate, but we increase the degree of the polynomial that we use to approximate, the error goes to 0. Polynomial approximations will converge to the true answer in the limit, in other words. So that's really useful. Finally, the last question for this exercise was to interpret this in terms of the relationship between our Taylor polynomial approximations and f of x. I just said some words about that, but I want you to write this out as an exercise. Give me all of your thoughts about how Tn and f compare in this particular example with sine of x as our function. So we're almost done here. Just have a couple more things to talk about. But this basically gives you everything you need to do in order to solve problems like this. By the way, here is a static image of the blue sine curve, and this looks like maybe a degree 5 or 7 polynomial. Let's see. 1, 2, 3, 4. It looks like it has 4 critical points. So that should be degree. Oh yeah, degree 5. It says right here. Degree 5 polynomial. They'll all be odd degree, keep in mind. And on the interactive version of these slides, you can slide this bar around and get better and better approximations by using more n values. If you go and use an online graphing calculator like Desmos, you can actually change the number of change n, the degree, and also change other things like the center of the polynomial. You can just live in Desmos, you can change the function you're approximating to. So there's some good graphical tools for studying these problems. Here's some main takeaways from our discussion of Taylor polynomials today. In order to understand how the error in our Taylor approximation changes as n increases, we really need to have an expression for the nth derivatives of our function. And in order to explicitly bound the error, we choose the worst case scenario for the next derivative, the n plus first derivative, on the interval that we're approximating over, and use that in our error bound formula. In general, Taylor polynomials become less accurate the further you move from the center of the polynomial. We saw this with the sine example a moment ago. But we can dodge this issue by choosing larger degree polynomials to make our approximations and having strict control over the potential error involved, depending on how far out you go in terms of x. There are some important caveats to all of these discussions, which is some functions just don't behave well when we try to approximate them. For example, here's a piecewise function that turns out to have infinitely many derivatives. We can take derivatives of this function everywhere. For the 2 branches of this piecewise function, the derivatives are computable, but at 0, you have to take a limit of the slopes of tangent lines to find that the derivative exists. But it turns out that that derivative is always 0, which is sort of strange. The e function is kind of coming in at such a slope that if you ever try to approximate slopes here, or concavity, or jerk, which is the third derivative, you'll always get an answer of 0 at x equals 0. So the Taylor polynomial is just the 0 polynomial, or a horizontal line, which no matter how large we take the degree of this, it's always a 0 polynomial. It will never get close to any positive x value function values. So we're never going to be able to accurately approximate anything for this function. Well, how can this be? We had Taylor's inequality telling us that, error is controlled by something or other. Well, the idea here is if you look at the error expression, the error bound expression has derivatives of f and values of x, and then the n plus 1 factorial business. But the derivatives of f are 0, so we can use m equals 0 as a bound, which says that, or rather, sorry, m is the derivatives. The derivatives of our function in this case, e to the minus 1 over x, grow without bound. So the capital M's we have to use there for those derivatives will increase without bound. And in particular, the error bound increases so that the error can never get smaller than any particular threshold we want. And this is true for any positive x. If you fix the x you want to approximate, you can always choose a high enough Rn so that you are so that you're not approximating closely. I'll say it that way. So here's some summary questions for you to think about, and then I'll leave you with a couple exercises. First of all, why do we use Taylor polynomials? What did you learn in this video that convinced you that these are a useful technique to know? Next, why is there a denominator with the term k factorial in the general formula for a Taylor polynomial? Explain why we'd always rather center a Taylor polynomial for the function y equals ln of x at x equals 1. And I'd imagine this means versus something like x equals 0 or other values. Or sorry, no, x equals 0 is undefined versus something like x equals 2. And finally, what properties make a Taylor polynomial Tn of x a better approximation of f of x compared to other Taylor polynomials? What makes a particular one a good approximation? Here are two exercises for you to think about. Question 6, I think, is just a fun paper and pencil exercise. See how well you can approximate these interesting looking numbers, or at least think about what strategies you would use to do this. And finally, here's another function to practice with, x e to the x, and the question asks you to compute a Taylor polynomial and bound the error. Oh, sorry, there's one more question. I'll just flash this one up. And this is a little more about under and over estimates for you to think about, since we haven't talked so much about that with Taylor polynomials. Thanks for tuning in, and I'll see you next time.